Welcome to this Conservation Applied Research and Development webinar today on right-sizing water distribution pipes and water heating systems to save energy and reduce building costs. We really appreciate those that are joining us today. I'll cover a few housekeeping items before we jump into the main content of the presentation. All attendees will be in listen-only mode. We will answer questions at the end of the presentation, but as questions occur to you, please do type them into the Q&A box and send them to all panelists. The Q&A box is located at the on your screen and can be opened by clicking the ellipsis in the lower right hand of your screen. We will do our best to answer all questions within the time allocated, but if we don't get to some, we will answer them after the webinar. This webinar is being recorded and will be made available on the department's website. The slide set from this webinar will be emailed to all registrants within a couple of weeks from today's broadcast, as well as will also be made available on the department's website. And finally, if you would like closed captions on this webinar, click the CC bubble in the lower left of your screen. I am Lindsay Anderson, the Eco Research Director at the Minnesota Department of Commerce. Here, I identify and analyze gaps within utility, energy conservation, and optimization programs, and I coordinate and plan research to fill those gaps. The CARD program, which funds today's research presentation, is a major tool of that work. I also was the department's project manager of this project and will be moderating the Q&A portion of today's presentation. Our presenters today are Elise Wall, whom is a senior consultant at 2050 Partners. There, she works on other hot water related research, manages cross-cutting topics on data structure, as well as supports the California statewide building energy modeling stakeholder group. We will also hear from Gary Klein, whom is the president of Gary Klein and Associates, where he consults on the connection between energy, water, and carbon. He has been involved in the development and implementation of right-sizing piping since 2011. Last presenting will be Mason Miller, a research analyst at Center for Energy and Environment. Mason deploys data monitoring equipment and provides data analysis for CEE's various energy efficiency research projects. Not presenting today, but still contributing significantly to the project are Steffi Becking, Director of Building Codes Practice at 2050 Partners, and Ben Schoenbauer, Director of Research at CEE. I'm really looking forward to hearing the presenters present today. This webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. Research areas are expanded with the passage of the Minnesota 2021 Energy Conservation and Optimization Act. The purpose of the fund is to help Minnesota utilities achieve their energy savings goals. $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD and CARD projects provide utilities with data to enhance energy efficiency program designs within their energy conservation and optimization portfolios. As you can see by the pie chart, CARD projects funded to date have been in all building sectors as well as some that cross multiple sectors. The subject of today's webinar is within the residential multifamily sector, and our presenters will share results from a recent CARD project which characterized the energy efficiency potential of right-sizing water pipes and water heaters in multifamily occupancies in Minnesota and informed a proposal on adopting the Uniform Plumbing Code Appendix M peak water demand calculator into the Minnesota Plumbing Code. Further, the project team will provide recommendations on considerations to further leverage the opportunity within the work to support utility energy conservation and optimization program implementation. So with that, without further ado, I'll turn it over to Elise to jump into the meat of the content today.
Hello, everyone. As Lindsay said, I'm Elise Wall, Senior Consultant at 2050 Partners. If you'll humor me, I'd like to start at the beginning and talk about how pipes are currently sized. When you're building a building, you don't necessarily know how much water the occupants are going to use, but conveniently, the code tells you, hey, this is how many gallons per minute your occupants are likely to use. So these are the size pipes that you should install in your building. So you go through this sort of algebra exercise. You convert fixture counts, so how many taps, how many baths, etc., to their equivalent quote unquote water supply fixture units. And then you read across this curve on the right here for the design peak flow rate, this gallons per minute number. Then you go back to the code and you use the peak flow rate that it predicts to determine the required pipe size. You can see here that curve C is for apartments, and that's what we'll be looking at today. So when Gary started in 2011, he and his team and the folks who work in that industry looked at this and said, well, this is a great prediction, but what if we could measure this in apartment buildings and plot the dots and compare them to this prediction here, what we're telling people to expect in their buildings? And that presented this very zoomed out curve. So this red curve is the Hunter's curve from the last graph for apartment buildings specifically. We went through and we found 20 apartment buildings, found their equivalent water supply fixture units, and plotted them on the same axes as the Hunter's curve. And we found even as you get all the way over here with so many water supply fixture units, we're not seeing this trend relationship that's claimed. This curve, Hunter's curve, was actually based on research done in the 1940s by, you guessed it, a guy named Hunter. And this was back when building philosophy was a lot different. So you had a lot more shared restrooms and fixture flow rates were a lot larger. So we're really just not seeing a payoff from sizing pipes according to Hunter's predictions. No one in this, even down here at 250 water supply fixture units, we're just not seeing the 100 gallons per minute that Hunter predicted would be demanded at the most by folks. And when I say demanded the most by folks, I want to talk about that for just a moment for some clarity moving forward. We use a metric called the peak flow rate, and it is the 99th percentile of flow rates in a building. And this is kind of a statistical, I want to be clear about it. So when you're designing plumbing, you're inherently trying to guess at the gallons of minute required by these future occupants. And statistically, it's really hard to guess the maximum demand. The maximum demand happens just about once exactly. And statistically, you're looking for general, populations or general representations of a thing. So because it happens so infrequently at the far end of the distribution, it's not really realistic to try and predict. Typically, when you're designing most processes in a building, you say, okay, well, I might not be able to predict the maximum, but I can predict the 99th percentile. So what is that 99th percentile? Where one time out of 100, it'll be exceeded, but 99% of times the demand will be equal to or lower than. We'll just have to accept that 1% of the time we won't be able to meet demand, and occupants will be, checking their watch and being like, well, all right, there it is. Okay. So we'll design for that predicted 99th percentile of demand, and we'll call it the peak flow rate. So this is the new device, I guess. It's a spreadsheet meant to update the method for pipe sizing. It's the water demand calculator, and it was designed by the International Association of Plumbing and Mechanical Officials, IAPMO. And unlike the water supply fixture unit graph, it's not a read-across problem. It's a calculator. It's made available in Excel, and you input your total number of fixtures here in the red box, and no need to convert them to water supply fixture units. It uses a statistical model, which is published, and you can dive into it if you want, but it's based on modern single-family home data, so observed data about how often folks use water to predict the flow rate. So this is not currently something you can use for plumbing design in Minnesota. The code says you need to use Hunter's curve. So for this project, we wanted to do 4 things. First, we wanted to validate the peak water demand calculator for sizing water supply pipes in Minnesota multifamily buildings. Remember I said that the water demand calculator was created with single family data and then extrapolated to multifamily. So we want to make doubly sure that it works for multifamily buildings. While we have robust data from other states, we wanted to confirm that buildings in Minnesota, which were not built using which were built using Hunter's curves, aren't somehow experiencing higher water demand than the WDC would have predicted if the WDC had been used in the design. So non-WDC buildings would demand the same amount of water that a WDC building would. So We'll take a look at them. We also wanted to estimate the potential savings in water, energy, cost, and carbon emissions from designing buildings using the WDC, and then explore what a code change proposal to initiate adoption of Appendix M, which is the part of the code that would allow the use of the WDC, into the Minnesota Plumbing Code. And just as chance would have it, fortunately, proceedings began during our project for the Minnesota Plumbing Code, which is never a guarantee. So I'll share more on that at the end of the presentation. We also wanted to take it one step further and start looking at the implications for water heating and the water heating sizing guidance. So when you're asking the question, all right, I got my pipes all designed, how big of a water heater do I need? We really want to avoid the costly oversizing of heat pump water heaters. And as the state moves towards electrification, heat pump water heaters are going to be essential. So unlike gas heaters, they can't be cost effectively oversized. So we wanted to understand the current oversizing practices and how the WDC might help reduce energy and water use. All right, with that, we're going to dive into each goal in more detail, starting with the first, validating the peak water demand calculator for the supply pipe sizing in Minnesota multifamily buildings. And for this, I'll hand it over to our partners at the Center for Energy and Environment and start out with Mason with some site descriptions.
Elise, we collected and analyzed data from 4 multifamily buildings in the Twin Cities metro area. 2 of the 4 buildings, those located in St. Paul, participated in a past GARD project performed by CEE to evaluate the performance of high-performance central water heaters. 2 additional buildings, Dayton and Richfield, were recruited, had instrumentation installed, data collected, and analyzed for this project. Buildings were selected to represent a range of sizes across small, mid, and large numbers of units. We also targeted buildings with different rental types, construction eras, and locations. The measurement and verification for each building were designed to characterize the cold water, hot water, and total domestic water flows. Ultrasonic flow meters were used to limit the intrusion on the building's operation and ensure the accuracy necessary across the full range of necessary flow rates. Plumbing layouts in the building and flow meter requirements for flow development required careful meter placement in each building. The final placements and instrumentation diagrams for each site are available in the final report. For each new building, we settled on measuring 2 of the indicated flows and calculating the third. For example, in one building, hot water flow and total water flows were measured directly, and the difference between the 2 measures was the hot water use. The data from previous research projects only measured hot water use, so those buildings only included hot water measurements. Each flow meter was field verified and calibrated if necessary. Calibration was done after the meter was installed by running a series of water draws of known volume and flow rate to be compared against the meter readings. This is a picture of the ultrasonic flow meter. While these meters allowed for flow measurements without cutting the pipe, insulation had to be removed to clamp on the meter as shown in the photo. The blue and red leads connect the meter to the data logger. The data was then transmitted from the logger to CEE servers for processing and analysis. In addition to flows, we also recorded various surface temperatures on several water lines in the mechanical room. The temperatures were primarily used to verify operation of the system and determine energy flows in the building. This table shows the summary data for monitoring at each of the 4 buildings. Each of the new buildings was measured for approximately 4 months, while the older buildings were measured for almost a full year. Data was collected at 1-second intervals. Each building had multiple water heaters to serve the hot water load of the building. The final building in the list, Richfield, Multifamily 91, shows that we did not measure the water use for all 117 units in the building. This building has 2 water distribution systems, one that serves the bottom 4 floors and the other that serves the top 11 floors. The 91 measured units were all the units connected to the water system that serve the top portion of the building. And with that, I'm done, and I'll pass it to Gary for the next few slides.
Thank you, Mason. All right, so what we're looking at here is a cumulative flow distribution for one of the buildings that we studied. It starts at 0 flow gallons per minute. It builds up to 100% of the total flow. The 99th percentile, as shown by the vertical red line, is about 5.4 gallons per minute. That means 99% of the time the flow rates are less than that. If you look to the far right, the water demand calculator predicted that the building's demand for hot water would never get over 16.5 gallons per minute. And in fact, all the red dots are less than that. I want you to also look over to the left of the graph where it says the 50th percentile. 50% of the time, the water flow on the hot side is less than a gallon a minute. It's much, much lower than we would typically think. The next slide, please. We did those cumulative flow distributions for all 4 buildings so that we could understand what was going on. And here we're looking at the comparisons between the black dots, which are near the x-axis, and either the WSFU estimates or the WDC estimates of peak demand. And we're trying to figure out how safe are our new predictions. If you look at the difference between well, let's look under Dayton MF 48. The over prediction of the water demand calculator, the water supply fixture unit method is about 8 times the measured peak. That's a huge margin of safety. The water demand calculator for that same building is around 2 to 1, a little less than 2 to 1. And in fact, almost always 2 to 6 times for the water demand calculator, still providing us a good margin of safety based on what we're actually measuring for peak demand. All of us involved in this effort want to make sure that we don't unintentionally undersize the diameter of the pipe, creating issues with flow rates in various fixtures. It turns out that we're looking at these peaks, these 1 percentile peaks happen from our measurements well under a minute in duration and very, very infrequently. The next slide, please. All right, now we're looking to see how the Minnesota buildings compare to all the other buildings we've measured of the same type. So this is all multifamily apartment buildings from different parts of the country. They range in size from, I think it's 8 to 384 apartments on the far right. And you can see what Elise likes to call the lollipops. The red one on the top is the water supply fixture unit lollipop. The blue is the water demand calculator, WDC estimates, and the black dots are the measured 99th percentile peaks. In all cases, we have a safety margin when using the water demand calculator. And you'll see if you look carefully at the top on the right, several of the buildings have WSFUs that are way off the chart. We decided not to make the chart that big. We just tell you that it's way oversized. Two of those were in Minnesota. So we've been using a method of sizing water demand piping that goes back to the 1940s. And shout out to Dan Cole, who brought this idea to IATMO in 2010, 2011, and we formed a committee to address this topic. He and his colleague Randy Lorge teach this stuff every day of the week, all over the country. And our effort here was to help make sure that we could see the validity of using it in Minnesota. Next slide, please. Elise, I think it's back to you.
That is back to me. All right, now we're going to move on to our second goal. If you remember, this project had 4. So now we've looked and made sure that the new pipe sizes wouldn't underserve the residences. So now let's look and see, all right, if buildings were built with the WDC, what potential water, energy, cost, and carbon savings would be brought to the state instead of using the traditional Hunter's curve sizing. So first, I want to sort of get in your head, how would smaller pipes save water, energy, carbon, or even cost? Well, first up, water. The logic here is that smaller pipes mean less lukewarm water is flushed by occupants waiting for hot water to arrive. I don't know many people who jump in the shower when it's cold or are waiting for hot water to do dishes, and oftentimes that water is wasted. For energy, that follows that less lukewarm water sitting in the pipes means that less hot water is heated only to be lost as waste and then needing to be reheated later. And then following the energy savings, less energy used to heat the hot water means that there's less natural gas, the primary method to heat water in Minnesota, used to heat hot water. And then finally, as first construction cost, just from a material perspective, smaller diameter pipes are less expensive to purchase and install than larger ones, as well as the expensive fittings and connections. But this project did not include the fittings and connections. It's just the pipe cost. So, all right, we took one of our buildings, Dayton MF48, and we nabbed its plumbing plans working with the building owners. And we actually took the plumbing plans and that followed Minnesota code and the Hunter's curve, and then recalculated the pipe sizing using the WDC. So at the bottom of the page here is an example. In a 3-bedroom multifamily unit, some pipe sizes were reduced from 3/4 inches down to 5/8, even down to a half. And then the last row here shows that sometimes code would still require a larger pipe just for the places where water is most significant or maybe critical. So code would still require a 1/2-inch pipe there. And we honored those requirements in our final calculations. So what did we find? Here are the results per apartment unit. So you can scale it a little bit more easily by building. But for water savings, each unit would save 345 gallons per year, which would lead to 6.6 therms of natural gas saved per year per unit, 0.035 metric tons of CO2 equivalent per year per unit. And then finally, the first construction cost savings would be at least $618 per unit, $618 per unit. It's important to note that these savings reflect only the initial installation. So these smaller pipes cost less to purchase and install, but the figures do not include the recurring savings from reduced energy use or the decreased costs of the smaller miscellaneous fittings. We did calculate the ongoing utility bill savings. They amounted to about $14 per unit per year, which we didn't consider significant enough to include in the headline results. So that's not shown here. Let's see here. I'll also flag it says per discrete instance. So for this, discrete instance is the card term for the lowest unit of, I guess, common denominator for a project. And for us, that's apartment units. Okay, so here is our zoom out to the statewide impact. We also wanted to understand what the impact would be if Minnesota builders were given the option to use the water demand calculator. Since using this would be voluntary, we didn't assume that 100% of builders would just instantly know that it was an option, take it up as a practice, and then instantly start building all their buildings with it. So instead, we modeled 3 scenarios based on the forecast 2026 multifamily construction, and we took 3 sort of guesses at it. The low and pessimistic adoption assumption was 10% of new units. That's that first row there. The most likely adoption, we put at 30% of new units would be built with this, since it does give cost savings. And the high adoption, boy, we would love to see it at 80% of new units using the WDC. So I'm just going to walk quickly through the most likely scenario, 30% adoption. This would be about 4,000 apartment units statewide, and here's what that could mean annually. 1.4 million gallons of hot water, 27,000 therms of natural gas, assuming natural gas water heaters, and 141 metric tons of carbon dioxide equivalents saved, and $2.5 million in construction cost savings across the state. Our third goal was to explore how the water demand calculator could be formally adopted into the plumbing code. Specifically, if you want to get technical, through the state bringing on Appendix M of the Uniform Plumbing Code into the Minnesota Plumbing Code. And that would allow the use of the WDC as an alternative to the WSFU or Hunter's Curve method. So, as I mentioned earlier, this project turned out to be great timing. When we began the project, Minnesota was already preparing for a plumbing code update, and in fall 2024, we supported St. Paul Regional Water Services, who submitted a formal request to the Minnesota UPC Ad Hoc Rulemaking Committee under the Minnesota Department of Labor and Industry. That was one of the early steps in the plumbing code update process. It has to go through the committee first. So the proposal received strong support from industry stakeholders and got letters of support from the Minnesota Plumbing, Heating, Cooling Contractors Association, and also from the Minnesota chapter of the American Society of Plumbing Engineers. The committee was able to review and accept the request for consideration. Sorry, they haven't reviewed it yet. This means that the WDC is now actively being reviewed for inclusion in the upcoming code update. That's the first hurdle that it's passed. The final decision is expected. Oh, probably should have been putting my bullet points out there. Final decision is expected by 2025, by late 2025. And if approved, the full Minnesota Plumbing Code update cycle is projected to conclude in 2027. All right, so now we're on to the fourth goal. In the first 3 quarters of this presentation, was about right-sizing pipes. I want to be really clear. Okay, cool. We talked about right-sizing pipes. Now I want to turn to right-sizing the water heater system. So we're specifically looking at the water heater central to all these apartment units, typically. But it doesn't have to be. But this fourth and final goal was to evaluate whether water heaters in Minnesota are being oversized. It's sort of considered common knowledge that oversizing is a costly issue, but it gives a margin of safety for building owners who don't want to make a significant investment in a water heater and then find that they get hot water complaints, that folks aren't getting what they expect. But this can be costly for heat pump water heaters, which can't be economically oversized in the same way that gas heaters often are. But when you're designing a new building, same as with the pipes, you don't know the actual water demand yet. You're making an educated guess and you want to be safe about it. So the ASHRAE, which American Society of Heating, Refrigeration, Air Conditioning Engineers, provides guidance to help builders estimate the appropriate water heater size. And we wanted to assess how well those recommendations align with actual hot water usage in Minnesota and whether or not they contribute to this oversizing in practice. Okay, so let's say we're building a building and we want to take a closer look at how ASHRAE is giving us this guess at how big of a water heater we would need for our apartment building. Builders don't know the actual water demand during design, so ASHRAE provides this framework based on a series of assumptions that us as the plumbing designers get to make. So first, we're going to estimate the building occupancy, how many bedrooms, and reasonable guess based on the count of bedrooms and expected residents. Now we get into the subjective stuff. So you select a demand level, low, medium, or high. ASHRAE recommends this based on demographic criteria, but we found these assumptions to appear outdated and rely heavily on lifestyle stereotypes. And as you see in the graph to the right, high demand assumes over 75 gallons per person per day, and low demand assumes under 25 gallons. So even the low estimate is high per person for use. If you work in this industry, go ahead and put in the chat or in the questions which one of these you think is realistic. Our partners at CEE report that typically Minnesota sees 12 gallons per person per day. So once you make your assumption, and I believe ASHRAE recommends that for multifamily you assume high use, next you choose a calculation method, either average or incremental. So I won't get into detail, but the average method is mathematically much simpler and gives a single recommendation. The incremental method, now you open the flow chart up into more assumptions, including selecting a peak hour, which ranges from 1 to 24, so a huge range. And it can be confusing why you would select a particular value. Ultimately, the point of the slide is just that the sizing outcome is very sensitive to these assumptions. And since designers don't know future demand, they're tempted to make the conservative assumption, which is what leads to oversizing, especially due to the range of these consumption assumptions. So trying to make that conservative assumption often makes heat pump systems seem far out of the project price range, and folks default to gas. Okay, this is my rainbow graph. Bear with me, I'm going to explain it. Now we're going to compare ASHRAE's sizing assumptions to the actual hot water use we observed in buildings. Specifically, this particular graph is for the Richfield building, top 11 floors, multifamily 91. So what this graph is showing is how we back calculated the needed hot water system performance based on the actual usage data. So it visualizes how well a hot water heating and hot water storage tank would actually meet demand across the building. I'm going to walk you through it. The purple line here represents the threshold where 100% of days had no hot water shortages, meaning the system met occupant demand every single day at the combination of storage volume and heat pump water heater capacity, so how powerful the water heater is. So, for example, any point along this line reflects a combination that would have fully satisfied it. Oops, not to the sad faces yet. So you could pick, if you, as a designer, you could have picked a 300-gallon tank, and let's just round up to 150 kilobtu per hour heat pump water heater, and you would have been bang on. You know, if you had room for a 900-gallon tank, you also could have picked that and gotten a less powerful heat pump water heater down under 100 kilobtu per hour. So you've got options here. But what we also want to take away from this graph is that there's an oversizing cost here. So if you ended up picking a 600-gallon tank and a 200 kilobtu per hour heat pump water heater, you would have been paying out the nose, and you're not really getting any benefit because folks weren't really demanding what that can supply. The corollary here is that you could have undersized it. You could have said, okay, well, let's just get a 50 kilobtu per hour heat pump water heater and a 300-gallon storage tank. You'd be running out of hot water and your occupants would be a bit disappointed. So that's also a sad face sign. But just to end this on a happy note, if you aim for 99% of days with full occupant satisfaction, which is the typical goal in plumbing design, you'd look for a system that falls along that red-purple boundary. But really anywhere within the red-purple and the edge of the purple is going to be considered a right size heat pump water heater system. So let's compare ASHRAE's predictions and recommendations based on our rainbow graphs here. So these are the two other buildings, just to make sure we look at everybody equally here. But the hollow teal points here are the ASHRAE recommendations under different assumptions. So they might choose a demand level and a calculation method that gives them these super high ones, or they might choose a demand method and a calculation that gives you a low one. So the triangles are low demand, the four-sided, I guess square and technically also a square, but tilted, are the medium demand assumption, and then the high demand is the circle and the crosshair. Let's see here. For example, so selecting a high demand result in ASHRAE recommends a very large water heater, potentially around 150 kilobtus per hour. And for someone who's trying to electrify with a heat pump water heater, that size might seem unrealistic or unaffordable, leading them to default back to gas. But our analysis shows that oversized systems aren't necessary. Even under the low demand assumptions, a properly sized heat pump system could fully meet the building's needs to that 99th percentile. And we see the same pattern in both of these buildings here, MF17 and MF23. Only under the least conservative assumptions, the low demand and the simplified calculation method, did the ASHRAE recommendation aligned with what we observed to be right-sized. So this highlights a key issue. ASHRAE's guidance is highly sensitive to input assumptions, and without real data, designers might err on the side of caution. So leading to oversized, more expensive systems. So I want to summarize our findings across all buildings. I tried to sum it up in a table. So each column here is a set of assumptions from ASHRAE, and each row is a building that we measured hot water in. So let's take a look. We found that using ASHRAE's low demand assumption with the average calculation method resulted in right-sized systems for all the buildings we studied. And this is just for the power of the water heaters, assuming storage could be made to fit. But even with what ASHRAE considers a best guess, MF91 would have been adequately sized, but the others would have ended up in undersized systems in this incremental method for too small, or for the low demand method. So as soon as you assume medium demand, some buildings end up with an oversized system, and under high demand assumptions, everybody is equipped with a water heater that's way too powerful than for what's actually needed. CEE has an ongoing heat pump water heater for multifamily project, and it's in the water heater design phase. And they found that the baseline data on existing systems is indeed showing that heat pump water heaters can be significantly downsized when the actual measured baseline data of water use was compared to the designs from the assumed loads. So very excited to see that project moving forward as well. Okay, so those are our 4 goals. I just want to wrap it up with a summary of our final recommendations. So to monitor the Minnesota Plumbing Code update, we recommend continued monitoring of the code update process, and that support is given as needed to help advance the adoption through the Plumbing Code update process. Since this will be voluntary, education and awareness is really going to be key to see savings. So launch WDC education and outreach for plumbing system designers. Many professionals may not be aware that it's an option, and our list of recommended vocations to be included in these education outreach programs is broad and varied, and many of them aren't easily reached through existing forums. So a dedicated outreach might be needed. Also, in exploring incentive programs, bundling the WDC demand sizing measured with heat pump water heater installations, since the WDC reduces the demand on the water heater, it might make it possible to size smaller and be more affordable. But it may not yield enough energy or carbon savings alone to justify a standalone incentive. It could still be this valuable add-on measure. The 2027 IECC group is also working on energy credits tied to specifically the use of the water demand calculator. And those could potentially be integrated into Minnesota's energy codes for both residential and commercial buildings. So we suggest tracking these developments closely. And then finally, since a lot of the sizing has to do with the comfort of the builder with the hot water distribution system, we recommend ongoing research into how plumbing distribution systems impact the heat pump water heater performance. Our hope is that this work would help equipment specifiers, suppliers, and installers better understand sizing and feel more confident in developing and deploying right-sized systems. So thank you so much. I'll pass it back over to Lindsay.
Awesome. Yeah, thanks so much, Elise and Gary and Mason, for your great presentation today. So that moves us over into the Q&A portion of today's webinar. And although Ben Schoenbauer, Director of Research at Center for Energy and the Environment, did not present today, he did join our presenters to support answering questions during the Q&A as needed. So at CEE, Ben leads a team of expert researchers, directs research activities there, as well as remains the principal investigator on many water heater performance, service water heating, and residential HVAC system focused projects, including one that Elise had mentioned today that CARD is currently funding. So with that, attendees, if you have not already done so, please type any additional questions in the Q&A panel and send them to us, and we will go and start going through those.
Lindsay, we actually have a question in the chat from Alexis.
Yes, I see that. Yeah, so Alexis asks, did this work look at how much longer occupants may need to wait for hot water to arrive with smaller pipes? If so, what is the time difference? If significant, what are possible solutions to keep occupants content and well served?
If you'd like, I'll take the answer to that one.
I think you've got the most data to back it up, Gary.
Yeah. So it turns out, Alexis, it's exactly the opposite. Most American adults are on the order of 1 cup of water's volume in 1/2-inch diameter tubing. Okay. If we went to 3/8 tubing, you would have 1/2 cup of water instead of a cup. If we go the other way, if you start with 3/4-inch pipe at 50 feet long, it's on the order of a gallon in plastic pipe, PEX pipe. And if you go to 1/2-inch pipe, it's a 1/2 gallon. If you go to 3/8 pipe, it's a quart. As the pipe gets smaller, there's less volume in it, so hot water will arrive sooner. Part of the question you're asking is, do we have a big enough diameter related to the flow rate of the fixture? And that has to do with ensuring that I'll get to your other question. It has to make sure that there's enough. You don't want too much velocity, but you want enough. And so when you size cold water pipe, you want no more than 8 feet per second, hot water pipe no more than 5. And so we right size in accordance with ensuring there's enough residual pressure at every fixture. But in general, smaller pipe gets you hot water quicker, all other things being equal. And you are approximately 1 cup per about 6 feet is the way to describe that, not 1 cup per foot. We are not very tall. Back to you, Lindsay.
All right. Okay. All right, next question. Would it be helpful if moving forward, designers measured existing building hot water use before selecting a heat pump water heater system? And for new construction, measuring a similar building?
Ben, I want to bring you in for this conversation. What do you think? No, Ben. Mason, how about you? Nobody.
I would say
Someone's
based
gone.
on the results from this project, it would be very helpful. Kind of back to the first few graphs that Elise showed, you can see that it helps to have some real data and help you decide what a new building, if they should get new equipment, or looking at a similar building, what you should do for sizing based on the water use.
Yeah, I agree with that entirely. Most projects for central water heating don't get replacements done in a week. It takes, several weeks, if not longer, to get permission, get the funding in order, get all the measurements needed in order to fit, get the product ordered. In that time frame, measuring the water demand for hot water would be extremely helpful so that you could do a much better job of finalizing the equipment size. And for new construction, if you're building a new apartment building and it's sort of similar to one that's down the street that you built a few years ago, I'd be using the one you built a few years ago to true up the right sizing for the estimates of both the estimates of the pipe diameter and the water heater size. Seems to me those would be very helpful.
Oh,
We
apologies.
have more questions.
Oh.
Go ahead, Ben.
I was going to say apologies for the technical difficulties there, selecting the wrong microphone. But yeah, as I agree with both what Gary and Mason said. I'll just throw to the reference Elise made earlier that we're doing this for heat pump water heaters in Minnesota right now, and showed water heaters based on before we collected data in our baseline measurement phase. It's water heater designs that were almost twice the size of what came back after we started collecting data in buildings. Small sample size, but shows the trend that we're talking about.
And to both of you, to Ben, I have another question. The sizing question it's for any water heater type, right? Our estimates of peak demand for hot water are old and based on information that's not current for real uses and flow rates. Isn't that right?
Yeah, totally. I think we focus on heat pump water heaters because the cost of oversizing is so much greater, but certainly is true for any water heater you would install.
Cool. So Lindsay, we have more questions in the chat.
Yeah, good. Thanks, Gary. All right, Hillary asks, what takeaways would you highlight for companies that manufacture equipment for monitoring water use in buildings?
Ooh.
Get involved.
Yeah, absolutely. The first thing that comes to my mind, and I hope Mason and Ben can expand on this, is that one of our limitations was that the sensors need at least a couple feet of open pipe to get more accurate measurements. And in some cases, actually, I think in every building, that limited which pipes we could measure, which is why we had to settle for measuring 2 out of the 3 possible flows in the system. So I'd highlight that. But Mason, Ben, is there anything else you'd want to bring up?
I would say that's pretty spot on in my experience. There's certain parameters you have to fit after, like bends and tees in the piping, to be far enough away from them, and it's different if you're on a vertical pipe. So I guess manufacturers just being aware of how tight these mechanical rooms are, and if they can consider that in how they design these things. It's good to obviously verify that the flows you're getting are correct, which we did. So we found that kind of those parameters didn't affect our data. But yeah, that's what I would say about that.
Elise, if I had my druthers, I would ask all plumbing engineers to start designing in measurement points as part of the fundamental I can't change it rules for the design of the installation of the new systems. We always are going to need to come back and be able to measure things. We're building very complex systems into buildings, and we put them in and we hope they work right. And we have a story from this project where we were measuring water use in one of the buildings and found that there were these, every 5 hours, we had these huge peaks that no one knew about. Ben or Mason, you want to report on that? for a second? The water softener in one of the buildings was just going
Yeah.
nuts.
Yeah, that's a great point, Gary. I mean, I think I'll just add on, I guess, with your comment about doing this instrumentation early too, is that it's much cheaper to do when you design the system than when you have to come back and do it in retrofit. But for the specific example, we installed monitoring equipment in one of our buildings, and the first look had very high design flow rates or 99 percentile flow rates. And so we looked at the data a little closer and quickly identified these huge, 500-ish gallon draws in the building, and took a little digging into the data and going on site and examining it and realizing that the water softening system was flushing and descaling the system multiple times a day, where we were able to reduce that to like once a week, which saved, almost, I don't remember the exact percentage, but it was like a significant percentage of the building's hot water use.
Right. On the thanks, Ben. I think on the water softener, one of the things we noticed was that when it got reconfigured, they didn't reconfigure it to not match the rest of the building peak. So there's lots of room for improvement. It didn't affect any operation in the building, that's for sure. But if something only has to happen once a day or once every 2 days, don't pick it during the morning rush hour, right? That would be another observation of why build on top of another peak. So I'm back to the point about the idea of monitoring. We are building complex systems. They need monitoring. Things go funny. Things don't get set up the way the engineer thought they were going to get set up. It needs to be checked. And having spaces to do that with as part of the design would be really helpful. So Lindsay, I see more questions in the Q&A.
Yeah, excellent. I'm going to move to Dan's question, then go back to another question, just to continue to hear from different attendees and their questions. Dan asks, do the data also reveal standards for recirculation rates for the hot water loop?
No, they don't. Funny question, Dan. It's a good one. So what's the flow rate of a recirc loop? Well, the correct answer is that if you're running a loop that runs 24/7, that's a big if in my opinion. But if that's the decision you've made, the purpose of the recirc loop is to overcome the temperature loss in the pipe when no one is using hot water. In particular, the losses on the return. The single best way to reduce the losses, well, there's a few of them. One, reduce the volume of water in the piping by relocating things in the building as part of the design so that hot water fixtures are closer to the water heater that serves them and closer to the loops if you're putting in recirc loops from the loops to the fixtures. It reduces the volume of water in the system, and that's a huge win in heat loss for the recirc loops. But the fundamentals are that if you reduce the volume, if you insulate better, continuous insulation as opposed to screen doors in the submarine at every joint, or at every pump or valve or whatever it might be, the better you insulate the pipe, the less heat loss you'll have for the loop. Ben, remind me, I think with the EcoSizer folks that we've been working with in Seattle, we've been coming up with, we're sort of a target of 100 watts per apartment was sort of a goal for the losses of a loop, whereas many today are over 250 watts per apartment. That kind of thing is a way of looking at it. And you work backwards to get the heat loss rates that the recirculation pump rates to make that happen. Isn't that about right?
Do we still have you, Ben?
Oh, sorry. Yeah, that yes.
Okay.
Okay. One or two more questions, and then I will close us out. So Hillary asks, what factors do you think led to building residents using less water today than was estimated in the 1940s? You mentioned communal bathrooms. Say more?
Oh, sure. So, oh, Gary, I'm just going to repeat the anecdote that you told me. So you can go ahead if you like.
No, so when Hunter did his research, which, by the way, if he published in 1940, probably happened in the 30s, but maybe early 1940. Dan Cole will correct us if we're all wrong here. But fundamentally, we only looked at a few different fixtures. At the time, toilets were one of the fixtures, and the flush volume of a toilet was a cubic foot of water back then. Today, national is 1.6 gallons per flush, not 7.5 gallons per flush. So fill rates vary because the valves vary and the flush volumes are much less now. Flow rates for all devices, whether there were standards in the US or not, have gone down over the last 20 years, 40 years since 1980, more than 50% compared to what they were when we started this process of looking at the sizing of water demand. And so people don't stand in line waiting for toilets to be used in most houses. Some buildings, yeah, when you go to an airport, sometimes you wait in line to use the bathroom. But with very few exceptions, certainly in residential applications, people don't wait in line much anymore. There's enough toilets and enough bathrooms for people to use. Not always true, but 99% of the time or more it is.
And it's just it's a fixture to resident ratio. Boarding houses were still in use and popular in the 30s and 40s, and not everyone had a bathroom. So if you were putting in a toilet or putting in a sink, it's the chances that it's being used at the same time as the one on the next floor up are really high. So you need to be prepared for double the flow rate of one sink. And nowadays,
Yep.
when you put in a sink, you're probably putting in a lot more sinks. It's a sort of a building philosophy and consumer demand problem.
Yeah, when we moved to the house we live in now, there were 3 of us and there were 4.5 bathrooms. There's still 4.5 bathrooms and we're back to 3 of us again. In the middle, we went up to 6. Lots of bathrooms.
Okay. All right. For our final question here, and then I will close this out. What more work has to be done to right size heat pump, I'm assuming water heater systems?
Ooh, so Gary is actually on a committee looking at that right now. Gary?
Yes, so for right sizing water heaters, we need to have a better understanding of the hot water demand loads. Much of the work that we've got for the water demand calculator was based on analysis of hot water systems in buildings, and we can show it's pretty much lower than would have been expected by the codes and other standards. So we still need more data on how to better estimate hot water demand so that we can true it up with heat pump water heater sizing. GPC 47 is the ASHRAE committee that's developing a new standard or guideline, I guess we're going to call that, for right sizing water heaters that are air source heat pump water heaters for central multifamily. If anyone wants to help us with data on buildings, that would be a really good thing to do here. Reach out to any one of us on this call, Lindsay for sure, and we'll figure out how to help you help us and help everybody in the industry.
Okay. All right. Well, thank you so much, Elise, Gary, Mason, and Ben, and attendees. If you have any additional follow-up questions about this card project, please feel free to contact any of our presenters directly, or you can reach out to me and I can connect you as well if you need that support. Just let me know who you'd like to get in contact with. The recording of this webinar and slide set will be available on the department's website through the Conservation Applied Research and Development webpage, which is listed on this slide, along with the final report and any other final deliverables in the near future. However, likely before then, the slide set will be emailed out to all webinar registrants within a couple of weeks of today's webinar. When the deliverables from this project are available, you can access and link to those resources from the Research Since 2020 webpage, which is circled in red on this screen amongst the lists of other CARD research projects and available deliverables for projects completed since 2020. Besides Research Since 2020, the department's R&D webpage has CARD program resources such as program background and grantee information, as well as provides web links through the left panel to Commerce's Actions and Regulatory Project Search for final reports, or to web pages of final deliverables of CARD projects that were completed before 2020. Finally, to keep abreast of upcoming CARD webinars as they are scheduled and other news related to the Minnesota Energy Conservation and Optimization Program, please sign up for our ECO updates through the Department EcoGov delivery. A live web link to subscribe will be provided in the follow-up email along with live web links of the other websites shared today along with that slide deck in the next week or two. The Gov Delivery sign up can be accessed on the CARD webpage as well on the department's website. Again, attendees, thank you so much for participating today. We really appreciate your interest in CARD projects. Registration is open for 2 more CARD webinars in October. On October 23rd, Center for Energy and Environment will present on their industrial electrification through heat pump adoption for process loads market study. You'll gain insights from screening criteria for industrial heat pump opportunities, learn about evaluations at 6 Minnesota facilities, and hear about successful applications, including solutions found at 3 food processing and 1 pharmaceutical site. The session will also cover estimated technical potential across the state and describe utility program opportunities. Then on October 28th, the Cadmus Group will present findings from their comprehensive economic impact analysis and cost effectiveness analysis of ECO, detailing net impacts on employment, labor force, economic activity, and disposable personal income. These impacts will be broken down by utility type, ECO program field type, and income qualification. Learn how these vital findings will inform ongoing and future ECO planning and development. And finally, again, do not hesitate to reach out to me or to Catherine Fair, my counterpart, if you have any questions or concerns on CARD or need the registration web links for the above webinars.